patient survives the surgery and the heart damage heals. So we want, number 4, we want the probability that survives and, I'm just going to shorten it, but the heart damage heals, right? So we want survives and heals. So this is 2 events, A and B. So what's that equal to? Well, that's equal to the probability of A, which is what? Probability it survives, times the probability what? Heals, given that the person survives. Right? So what's the probability that, well, this is what we want, what's the probability that the person survives? What does the doctor say about the chances of survival? 60%, right? So that's 60%, or 0.60, multiply, what's this? It's 50%, isn't it? Because the doctor says, if you survive, given that you survive, right? The first event is that you survive. This is a conditional probability. He has 50% of the heart damage will heal. So this is 50%, and that multiplication yields what? Is that right? Yeah, 30%, right? That's not wildly reassuring, actually, but nonetheless, okay, 2 things are going to happen here. All right, number 5. Help me out on number 5. What's 5? Let me scroll down a little bit. This is back to a table like we did before. Okay, you've got 146 families, okay, we select one at random. What's the probability of not taking a vacation? Okay, so let's say no on vacation. Probability, I select family at random and they're not taking a vacation. What's that probability? So no vacation, right? 45 out of what? 146? What's the probability? Select their family at random and they own a computer. Probability of computer. Chase? Own a computer, 115 out of 146, right? 15 out of 146. What's the probability on C taking a vacation given that they own a computer? So this is probability vacation given they own a computer. Tyler?
87 out of 115.
Where did you get the 87 from?
Well, you have to take into account that they own a computer and that they're taking summer vacation. So.
Top row, right? Only the top row, right? So 87 out of 115. Everybody see where those 2 numbers came from? All right, how about taking a summer vacation and owns a computer? So, how about a vacation and computer? David? One family at random, they have to meet 2 criteria, right? How many of them are there that meet both of those criteria? That,
87 out of 146.
yeah, 87. Out of 146, there's 87 people that meet both criteria, right? They are going on a vacation and they own a computer. These 87 people out of all 146 people, right? I'm gonna let you guys do the last one, but I want to talk about the multiplication rule on the answer Nick just gave me for a second. Let's just look at this. Now, you did a really good job of simply looking at this grid and saying, oh, I can see the 87 people that meet both criteria, vacation and own a computer, and there's 87 out of the 146. But let's apply the multiplication rule just to kind of verify. If I, for some reason, didn't know that, and I applied the multiplication rule, I could say, all right, well, what's the probability of A, which is vacation, times the probability of computer given vacation. And the hope is that even if I apply that multiplication, well, I get the same answer, right? In other words, I should be able to get the same answer. So let's just take a look at it. What's the probability of vacation? Probability of vacation is 101 out of 146. Probability of vacation, 101 out of 146. What's the probability of owning a computer given that I'm going to take a vacation? Given that I'm going to take a vacation, that's these people. Probably own a computer. Well, there's 87 in that column out of the 101. So that's times 87 out of the 101. So there's no great magic, but it just verifies to us that the rule will give us the same answer, because sometimes you're not going to have the whole grid. You're not going to have a two-way contingency table. It might be written in words like it was written in the Ford problem, or the one about the heart surgery, okay? But the formula or the rule is working, you know, again, regardless of whether or not I have the grid or not. That makes sense to everybody? Yeah, Tom?
So, I thought that the way you can determine if it's dependent or independent was if it was P of B given A equals P of B.
I can, and that would be part of the next part, which would be part E, right?
Oh, that's what I was looking at.
No, this was just a quick departure on part D. This was doing part D two different ways,
Okay, sorry.
okay? But if I want to figure independence, you're absolutely right, I have to use, well, let's take a look at it quickly. You raised the question. So well, this is all D. Go on to E. This is are the events owning a computer and taking a summer vacation this year independent or dependent events. So we can look at, okay, what's the probability of owning, I guess the shorthand would be just put computer. Given vacation, is that the same as probability of how do this is the probability of B given A, is that the same as just the probability of B? That's our test for independence. Yeah.
And you can inversely use P of A given B equals P of A
Right, that's right.
as well.
Yes. So this is the test for independence. All right, so let's take a look at it. What's the probability? Well, what's the probability of owning a computer? Probability of a computer family is right here, I put 115 over 146. What's the probability of owning a computer given that I take a vacation? I think we have it backwards here. What's the probability, what I was saying, given that I'm going to take a vacation, 101 people, what's the probability of owning a computer? 87 out of the 101. 87 out of 101. And I mean, I can't tell without getting a calculator out. Are they equal or are they not equal? They're not equal, right? They're not equal, so they are not independent. Is that's part E. Okay? All right, let's read over, and you guys should try the last one, but I don't think we'll talk about it all that much, but make sure you understand problem number 6 and work a couple of the problems in the textbook, but let's look at problem 6. 16 batteries are tested.